This is a tutorial for Chapter 12 of Silberschatz database book, 6th edition. In particular, there is a figure 12.3 on page 543 that gives estimates of selection query costs based on various algorithms. And I'm going to go through 3 of them in this brief tutorial. And we will do some more in class. But it's very important that everyone in our class understand how to arrive at the query costs that are indicated in figure 12.3. So hopefully with this and the time in class, we'll have some clarity on it. We're going to start with the first one, A1. Algorithm A1, linear search. There are 2 different ones. We're going to look at the first one, the first row in the table. Hopefully you have the table in front of you. A1, linear search is the one that we're working on. So what we're saying here with linear search, first of all, is notice the file. In our assumption here, the file is not ordered on the search attribute. Otherwise, we might not need to use a linear search, but we're going to assume that the file is not ordered on the search attribute. It might be, but using this algorithm, we assume that it's not. So therefore, we are going to have to search all of the blocks, because the second assumption is that this is a non-key value, which in the context of this figure 12.1 means not unique. Okay, not unique. And so if we take a look at a particular column, which you notice here I've indicated is called alpha. Okay. Well, what are we looking at here? First of all, this is our the whole thing that you see here is the table. This is a block. Okay. This whole thing is the table or relation. This is an attribute which we'll call alpha. Okay. And there are, of course, other attributes here, 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 and here, whatever they are, okay, for this particular table. We don't care. We're going to search on attribute alpha. And each one of these, of course, is a tuple. There's the first tuple, second tuple, etc. And so we're assuming we have multiple tuples per block, as you see here. So there's a block that I've already marked. Here's another block. This is another block, all the way down, and we're going to call this block down here, we'll call this one at the top, we'll call it block 1. See this? Block 1. And down at the very bottom, this block, we're going to call this block B sub R, just for the purpose of matching the values that they have in the textbook. So since we've said that we're not searching on a key value, right, non-key value, therefore they are not unique. If we want to do a selection, here's a selection on the table where alpha is equal to, let's say, x. What that means is maybe I have, looking back at the table, see that? Maybe I have x here, maybe there's another one here, and maybe even in the last block I have another one. Okay, so in other words, there are tuples scattered throughout this table where alpha equals x. And so what is the cost of this query? Well, what we'll do is, first of all, if we say the seek time is T sub s, okay? And 2, the block transfer time is t sub t, like so. Then what is the total cost? Well, we want to find every place, remember this is our query right here, everywhere that alpha is equal to x. Well, clearly, since the x's are scattered throughout the whole table, and we have no index, remember we're doing a linear search, so we're going to have to look at every single block, load it into memory, and see which tuples match, and then go on to the next block. So we have to scan all of the blocks. So how will we do it? We will start by seeking to the beginning of this block, the first one. You see this block here, okay? So we're going to seek there, and we're going to transfer that block. Now we don't have to seek to the next block, because having transferred that block, we're already set for that. There's no seek involved. So we're going to transfer the next block, and the next block, and the next block, all the way down, scan all of the blocks until we get to the last block. That's very easy. This is the simplest problem in the world, right? We start at the top, we scan all the way to the bottom. So therefore, the total, let's try that again. The total cost is what? The time for a seek plus the time that it takes to transfer one block times the number of blocks. And remember, that's b sub r times b sub r. That's the total cost for this case. What was the case? This is A1 linear search. The file is not ordered on the search attribute. We have a non-key value. In other words, they're not unique. Let's look at the next case. Let's call this case A1.2, if you will, another linear search, but this one is going to be different. In this case, it's equality on a key, and where key means, in this context, that for any attribute, in this case attribute alpha, alpha equals x is true for not more than one tuple. Could be true for 0 tuples, or it could be true for 1 tuple. In other words, if I'm doing a select where alpha is equal to value x, then in my table, x is going to occur somewhere, let's say right here, where I just put it, okay? So this is true for that tuple, but it's not true for any other tuple, okay? So somewhere in this table, there either is a place where alpha equals x, or there's not a place where alpha equals x, but there's not more than one, okay? So each tuple then has a unique value for alpha. That's the point. So what are we going to do in this case? You can figure it out pretty easily that since it's not ordered by alpha, we may have to look at every single block, or we might not. What if it was in the first block, right? This is the first block, okay? This is block 1. And down here at the bottom, remember, this is block B sub r. So it could be in block 1. Let's look at block 1 up here. What if it were right here? Then if we start at the first block, block 1, we load that, we find the value for x, we can stop because we know that there's only one. So if we found it there, we're done. On the other hand, we could end up having to scan every block until we get all the way down here to block B sub r, and we look in there and maybe we find it there. Or maybe we don't find it there. Maybe it doesn't exist in block B sub r, so only when we get to the end do we know that it doesn't exist in the table. okay? But let's take the simple case where it exists in the table. We're going to assume that it's somewhere in the table. So we're going to seek to this place up here, to the first block. And then, that's the first step. And then the second step is to now scan from block to block until we find it. So you can see immediately what the time is going to be for this one. In the case that alpha equals x exists somewhere in this table, we're going to have the time for a seek plus, well, how many blocks do we need to transfer? If we find it in the first one, we only have to transfer one block. If we find it in the last one, we have to transfer b sub r blocks. So in the mean or average case, we'll get about halfway through the table and we'll find it. So we have the time to seek plus the time to transfer b sub r blocks. What is that? That's b sub r times t sub t, but divided by 2. Why divided by 2? Because on average, you will scan about half the table before you find it. Now, this is the answer that you will see in the textbook and in the textbook table. What they did not consider, of course, in that is what happens if if perhaps there is no tuple with alpha equals x. If you're doing lots of searching through this table using this algorithm where tuples don't exist, you have to scan the entire table because it could be in the last block. And so it would approach the time for this search here, right? In other words, instead of the average being somewhere in the middle, so b sub r times t sub t over 2, it would be skewed a little bit. But we're not worried about that. Just pay attention to this and how we got it. Okay, so now on to a third example, and this one's a little more complicated. We'll do some more of them in class. I'm skipping A2 right now. We'll do that one in class. But let's do A3 first, okay? And A3 is where we have a primary B plus tree index, okay? And we're looking for equality on a non-key, okay? In other words, equality is on some value that is non-unique, okay? What does that mean? That means we could have 0 or more tuples that match. But let's assume we have at least one tuple that matches. So what does this actually look like in the table? Well, first of all, notice it is a primary index, okay? Now you remember our discussion about primary and secondary. What is a primary index? It means the file is ordered with respect to what we're looking for, okay? So that means this file is ordered with respect to alpha. Let's look at the table, okay? Here's alpha. What are we doing? We're doing, again, selection where alpha, that looks kind of bad. Let me do that again. My sigma looked bad. Selection where alpha is equal to x, and that can be more than one match. So, for example, let's assume that that my x's are in this block, but it could be more than one block. Maybe I have some more. And maybe I have another x there, and then I'll let these values be null. Now this would be a reasonable way to organize a file like this, where each block has one. Now this is some different value here. This might be y, okay, in this block. And these down here might be z, and maybe those are null. Okay, so basically then, these are the blocks that I'm interested in. How do I know that my x's are grouped together like this? Because it's a primary index. It's a primary index, so things are going to be ordered by this. Now I know that x is before y, but just take those as abstract values. Okay, this one comes before this one, which comes before this one. Okay, now then, with a primary b plus tree index, what does that look like? Well, you know what a b plus tree looks like. I've got a root somewhere, and I'm going to make this a fairly simple b plus tree just because we don't have a lot of room. Why don't we just have 3 levels in our tree? Maybe we'll draw it like this. Okay, so maybe like this and like this, something like that. Okay, so let's see. Over here, perhaps, I'll have a pointer here, a pointer here at the beginning, right? That one is going to lead to here. Maybe the second pointer then goes to here. The third pointer here goes where? To someplace in here. Okay, and you've got more and more pointers. Finally, the last pointer that's occupied here, that one points maybe to our last block. Okay, so something like this. So the blocks that I'm interested in, as we said, are these blocks from here to here. Okay, so how do I get there using the index? We're assuming that the index is on disk as well, right? So the first thing I do is I seek to this. Remember, each in a B plus tree in a database, each one is consuming a block. So I'm going to seek to here, and then I'm going to determine which pointer to follow from there, and that's going to give me a new block. So I have to do a seek, and I have to do a block transfer, right, to get the root. Then I'm going to do from here another seek to get this node, another seek, and another block transfer. What about this node? Same thing. That's another seek and a block transfer. And then that's going to give me then, this is the pointer that I want to follow. I've determined that once I loaded the block into memory, and I know now where I want to go and get the data. So let's just figure out that part of it. How much time does it take to find where the data starts in the table, which is, of course, with this block right here. How much time does that take? Well, we'll say let h sub I be the tree height of the index. Okay, in this case, what is it? It's 3, right? 1, 2, 3, right? Okay. So h sub I is the tree height of the index. So then the cost for learning where in the table to start, what is that cost? Is h sub I, that's the height of the tree, times the time that it takes for a seek plus the time that it takes for a block transfer. Why? Because for each of these, for each level of the tree, I'm going to have 1 seek and 1 block transfer. For this level, 1 seek, 1 block transfer to load this one, right? For this level, 1 seek, 1 block transfer. So h sub I times t sub s plus t sub t. Very simple, okay? But we're not done yet. We only know where in the file to look. We haven't actually found our values yet. So let's say right here I've got 3 different blocks that contain my value where alpha equals x. But let's make it general. Let's say that this is B number of blocks. Okay? So, scrolling down a little here, let B be the number of blocks containing tuples where alpha equals x, right? The cost then of reading all tuples where alpha equals x is therefore going to be what? You know we have to do a seek to get to the first block, this block that I'm marking here, right? This block. We have to do a seek to get there. So we have one seek. Then we have to read it. That's a block transfer, but then we're going to keep reading until we run out of x's. So it's B number of block transfers, right? So this is really easy. The cost of reading all tuples where alpha equals x is the time of a seek plus B, remember we said B number of blocks, this is B blocks right here that contain x. So B number of blocks times the time that it takes to do a transfer. Okay? Now then, just so that I'm clear, I will even change color. So we've got the time to read the index is this much. See that? And then once we have that, we know where to start. Here's the time to actually read all the blocks that we need. So the total, right? The total time or cost is, let's get the top part, h sub I times t sub s plus t sub t, okay? That's the part to read the index, plus t sub s plus b times t sub t. You see, that's just this part, and this other part here is just this. Okay, so in other words, this is the time to read the index, and this is the time to read the table blocks, right? Time to read the index blocks, time to read the table blocks. And I think if you take a look at it, you'll see that matches what we have in the book for each of the three that we have covered. So I hope this helps. We will do some more in class on Wednesday, but I wanted to make sure that you had some introduction to it and could begin thinking about it before then. So we'll see you all on Wednesday.